I'm Helna Mary, a second year PhD candidate student from Northeastern University. First of all, thank you for this opportunity to present my work on targeted delivery of IL-1Ra mRNA using cationic peptide modified exosomes for cartilage repair. Exosomes are nano-sized membrane-bound vesicles that are packed with genetic materials, growth factors, proteins, and other bioactive metabolites. The biocompatibility and low immunogenicity of exosomes make them an ideal carrier for gene delivery compared to the current viral vectors or synthetic lipid nanoparticles, because these carriers are known to cause viral genome integration and other safety concerns. Recent studies have shown that MSC-derived exosomes have cartilage repair properties. For instance, here the intra-articular injection of MSC exosomes into DMM mice 4 weeks post-surgery rescued the cartilage from degradation significantly better than the control group as shown in the Saprin O images. Therefore, MSC-derived exosomes have intrinsic therapeutic potential, and here our goal is to use them as carriers for gene delivery to cartilage. However, the cartilage is a dense matrix of negatively charged aggregates, which gives the tissue a high negative fixed charge density. This, in combination with the meshwork of type 2 collagen, restricts the pore size of the cartilage to 10 nanometers, but the pore size increases by 100 times in an arthritic cartilage due to the loss of gas. Moreover, the negatively charged lipid bilayer of the exosomes are electrostatically repelled by the anionic cartilage matrix, which hinders their penetration and transport into the deep zones. This high negative charge of the cartilage provides an opportunity to enhance the drug targeting and transport. So our lab has specialized on developing optimally charged cationic biomaterials such that they enable weak and reversible binding and thus allow faster diffusion along the cartilage thickness and higher uptake. However, too high of a positive charge will hinder the diffusion of the carriers due to strong binding interactions. Therefore, our goal here is to synthesize cartilage targeting charged reversed cationic exosomes that penetrate through the full thickness of cartilage and target chondrocytes for effective gene delivery. Based on these concepts, our lab has designed a short-length arginine-rich cationic peptide carrier with a net charge of plus 14. And CPC plus 14 have demonstrated full thickness cartilage penetration and 400 times higher intracartilage uptake compared to its neutral counterpart. So to design cationic exosomes, our approach is to surface modify them by anchoring the CPC plus 14 to facilitate the cartilage penetration and chondrocyte targeting in the deep tissue. So to this end, we harvest the exosomes by using differential ultracentrifugation and size exclusion chromatography. Exosomes were then anchored with CPC using DSP PEG lipid insertion. So the hydrophobic part of the lipid is inserted into the lipid bilayer of the exosomes, and then using copper-free DPCO chemistry, CPC was conjugated to the hydrophilic part of the lipid. The TM images confirm that the size and the morphology of these exosomes were not altered post-surface modification, and the net charge on the exosomes was successfully reversed and brought close to the neutral charge. Moreover, the labeled cationic exosomes demonstrated full depth penetration in an early stage arthritic cartilage explant model compared to the unmodified exosomes. To assess in vivo cartilage transport, labeled native and cationic exosomes were intra-articularly injected into mice knee joints 9 weeks after the DMM surgery. The sections of tibial and the femoral bones were imaged on day 1 post the IA injection of exosomes. Unmodified exosomes did not show any fluorescence, whereas the cationic exosomes exhibited significantly higher fluorescence through the full thickness of the cartilage. To demonstrate the application of cationic exosomes for gene delivery, we used EGFP mRNA as a model gene. And the mRNA loading was done with a chemical transfection reagent, and it resulted in a 20% loading efficiency. Cationic exosomes showed higher transfection efficiency with higher GFP expression in the human chondrocyte cell lines compared to the unmodified ones. We further assessed the targeted mRNA delivery by the exosomes in the same DMM mouse model. And the native exosome showed only minimal GFP expression, whereas the cationic exosome showed significantly higher GFP expression in the deep cartilage tissue. Similarly, we also studied the effective mRNA delivery of the cationic exosomes in human cartilage tissue. So the explants that we harvested from the donated human talus bones were treated with interleukin-1 to simulate arthritic condition by inducing 20% campers. Consistent with the in vivo data, cationic exosomes showed 4 times higher GFP expression through the full thickness in human cartilage compared to the unmodified exosomes. We then selected interleukin-1 receptor antagonist as a potent disease-modifying gene. We custom synthesized the IL-1Ra mRNA by in vitro transcription method and evaluated its bioactivity in IL-1 challenged human chondrocytes. A dose-dependent increase in the levels of secretory IL-1Ra protein was observed with an 80-fold increment with respect to the control group. In a similar cytokine challenged human cartilage explant model, we studied the targeted IL-1Ra mRNA delivery by the cationic exosomes. And the positive IL-1Ra signal, here shown in green color, was observed in higher number of chondrocytes, which was delivered by the cationic exosomes compared to the unmodified exosomes. Thus, to summarize, for the first time, we developed charge-reversed cartilage targeting cationic exosomes for effective mRNA delivery by harnessing electrostatic interactions with the anionic aggregates. Cationic exosomes demonstrated full depth cartilage penetration in DMM mice, followed by an intra-articular injection, while the native exosomes did not. Moreover, cationic exosomes enabled superior GFP mRNA expression in the DMM mice joint and also notable IL-1Ra mRNA expression in arthritic human cartilage. Hence, these cationic exosomes hold the potential to be an ideal non-viral nanocarrier platform technology for cartilage-targeted gene delivery. Finally, I would like to acknowledge my advisor, Dr. Ambika Bajpai, my collaborators from Rush University, Dr. Rachel, Dr. Anne Mary, and Dr. Susan, and the funding resources, and also the members of Molecular Bioelectrostatics and Drug Delivery Lab at Northeastern. Thank you, and I'm open to any questions.
Can you introduce yourself briefly?
Ted Nyans. Did you detect any, so in the DMM mice intraarticular injection model, did you detect GFP expression other non-chondrocyte?
Sorry, can you repeat the question?
The GFP expression in non-other chondrocytes, different cell and
No, we haven't looked at that.
Hi, my name is Cartilage Repair from the University of Michigan. Great talk. I was curious about if you guys investigated the degree of functionalization on your exosomes with the CPC and how stable that functionalization is with the lipid PEG.
So, with the surface modification of CPC on the exosomes, we have more than 400 cationic motifs on the exosome surface. And regarding the stability, we have ensured the stability in low, like in a pH of different pH buffer solutions, and we have seen that the lipid insertion was stable and the exosome size or the zeta potential were not altered in different pH solutions. Yeah.
Thank you.
Petri Tanska from University of Eastern Finland. Terrific work, thank you. I was just thinking that what was the time to reach the penetration of the deep cartilage? And have you tested, or what is the difference between have you tested what is the difference between a healthy and arthritic human cartilage with the penetration time?
So, all this data that we show in terms of the cartilage penetration and also the GFP expression in the DMM mice, These were imaged like after 24 hours of the intra-articular injection. So that 1 day is sufficient enough for all the cationic exosomes to have a deeper penetration. And moreover, we have also looked at the in vitro cartilage transport in bovine explants with a thickness of 1 millimeter, and we have observed that these cationic exosomes were able to penetrate in the deep zones within 4 hours of incubation.
Quick question, Bill Wall from University of Boston Medical Center. Do you observe any extra articular distribution of your exosome?
We haven't really done the biodistribution study of the cationic exosome, but this would be an aspect we would want to pursue as the next step.
Thank you. Thank you.